Okay, so Kolmogorov's axioms, and this is the modern axiomatic approach to probability theory. Okay, so here are the axioms. There are only 3 axioms. All we need to do is make 3 assumptions, and then we can create the theory of probability based on that. So let's let S be a sample space associated with an experiment. Remember, sample space is the collection of all possible outcomes, right? We are going to say that for each event A, remember an event is a subset of the sample space. For each event A, there exists an associated value, P of A, where P of A is a non-negative real number. This is called the probability of A, satisfying the 3 axioms of probability. And what are the axioms of probability? Number 1, the probability of A is a real number which is larger or equal to 0, less than or equal to 1. Assumption number 2, the probability of the sample space is 1. I mean, does it make sense to assume that the probability of A is between 0 and 1? Yeah, because, the probability of 0.4 would mean that the likeliness that the event A occurs is 40%, right? So making P of A between 0 and 1 makes perfect sense. The probability of S is 1. Does that make sense? Well, the sample space contains all possible outcomes, right? So if you carry out the experiment, there will be an outcome, and therefore the sample space has to occur, right? So it makes sense to assume that the probability of the sample space is 1. Now, sample space itself is an event, right? Because sample space is a subset of itself, right? So it is an event itself. And the third assumption is the following. For any sequence of mutually exclusive events, E1, E2, E3, mutually exclusive means the intersection of EI and EJ is empty for any I not equal to J, right? Of course, if I and J are equal, right, then you have the same event. The intersection is the same event, right? So for any sequence of mutually exclusive events, E1, E2, E3, the probability of the union of the events EIs is the same as the summation I going from 1 up to infinity of the probability of EI. The probability of the union of EI, where I goes from 1 to infinity, is the same as the summation I going from 1 to infinity of the probability of EI. Okay? The key here is that these events are mutually exclusive. Okay? So these are the 3 assumptions. Now, does number 3, is number 3 sort of, do you feel like that it should be true of probabilities? Well, the events are mutually exclusive, right? If you have mutually exclusive events, right, you would expect the probability of the union to be the sum of the probability, sum of the individual probability. Right? Is that making sense? So, based on these three assumptions, then there are some immediate immediate consequences that we can write out. So my first result or theorem based on the three axioms is the following: the probability of the empty event must be zero. This isn't my assumption, right? The probability of phi is zero. That's not one of the assumptions. So I want to show you that the three assumptions that I have laid out, based on that, we can conclude that probability of phi must be zero. Okay, so how is that? So let's try to prove this. Let's try to prove this. Why is the probability of the empty event zero? Why should it be zero? Well, I mean, intuitively we know that we want it to be zero, right? But how do I prove it based on my three assumptions? Well, which assumption should I be applying here? Let's do the following. Let's define a sequence of events. So let's let E1 be the event, which is the entire sample space S, and let's take E2 be equal to E3, be equal to E4, be equal to ... So basically I'm saying I have a sequence of events, infinite sequence of events, where the first one is the sample space and all the other events are the empty events, are all empty. So let's now apply the third assumption that we had. So according to the third assumption, by axiom 3, what can I say? Let me make some space here. I feel I'm going to need that. Okay, so by axiom 3, notice that the probability of S, first of all, would you agree that the union of all EIs, I going from 1 up to infinity, the union of E1, E2, E3, is exactly the same as S, right? You agree? S is the same as the union of E1, E2, E3, right? Because E1 is S and all the other ones are empty, right? So the union of them is exactly S. So I can say this equation that I have. Right, now I apply axiom number 3. By axiom number 3, this is the same as, are these events mutually exclusive? Obviously they are mutually exclusive, right? What's the intersection of EI, EJ? Intersection of EI, EJ is empty, so they are all mutually exclusive. So I can apply axiom 3 now and say this is the summation I going from 1 up to infinity time of the probability of EI, right? Are we okay so far? Okay, now this summation, I'm going to write it as the probability of E1 plus the summation I going from 2 to infinity, the probability of EI. So what I did is I am writing the first term of the series separately. So then, so far what I have is probability of S. What is the probability of E1? Remember, E1 is exactly S. So the probability of E1 is probability of S plus this summation that I have here, right? Notice that every single EI there is the empty event, right? So notice that the EIs are still mutually exclusive. So again, apply axiom number 3, but in the reverse direction. So I can say that this sum is the same as the probability of the union, I going from 2 to infinity of EI. So this is where I applied the axiom in reverse. And so now I have the probability of S is equal to the probability of S plus, what is the union of the EIs, I going from 2 to infinity? Well, since I goes from 2 to infinity, each EI is empty. Therefore, the union is empty. So this is exactly the probability of the empty event. Well, now it's clear. Now you just cancel out P of S from both sides, and what you get is that the probability of the empty event is 0. Is everybody okay with that? So we got that the probability of the empty event must be 0 from our axioms. Okay? So all I used is, all I needed to use are just the axioms to prove that.